Welcome back to ECE 501B. Our last two homework assignments are listed on this page. They aren't yet available on the website, but homework 7 should be there, and homework 8 will be there shortly as the plan. Your project deliverables are due the same day as your last homework. Hopefully you'll be able to juggle all of those different activities that are due on the same day. So you can drop them all come December 7th. You can turn them all in, is what I mean, in the Dropbox, or it used to be called the Dropbox. The final exam is on Tuesday of December 13th, and it's at 6 o'clock is when it starts, and it will be a 2-hour final. And as I said before class, luckily we have a large audience today to make a meaningful vote. And now I don't know if we have an electoral college or if we want to just take, never mind. But do you want to meet on Wednesday? I will probably, if we do not, I will give you a little bit of a material on the singular value decomposition that you can look at and watch on that. So do we want to be here? Judging from the attendance today, we may not have any larger of an attendance on Wednesday. Do we want to just go ahead and say no class on Wednesday? Is that all right? So tell your friends and colleagues that the vote has been collected. All of the electronic ballots were monitored properly, and we will not be meeting physically in class on Wednesday. But watch for the material on D2L. What I want to do today is finish this discussion of polar decomposition, and it's really a intuitive understanding of how we can think about operators. We can break it up into two pieces. One is this rotation piece, which is the isometry, and the other piece is the scaling piece. And the nice thing is we can actually decompose any linear operator in this way. And what we want to do is finish up that discussion. Then we will get into singular values, and as I suggested, I might provide you with some additional material for the time period if you really want to have a 501B hour on Wednesday. Hopefully I will have that available to you, but you won't have to come to class to have that. It will be online or on the D2L website. But singular values are very important, and for that reason I didn't tell you what the number was on the theorem. It's so important I wanted to be able to write that down in place, but that should be Theorem 51 in Chapter 7, the singular value decomposition. We now have a U matrix and a V matrix. That's made up of orthonormal vectors, and they're not in the same, or they're not the same vectors generically. So we actually have these two different sort of directions associated with, and now we can think about not just an operator but a map. Now we can generalize this to have different dimensions in the input vector space and the output vector space. But V is associated with those vectors in the input vector space, and U is associated with the directions or the vectors in the output vector space. We'll hopefully be able to get a little bit better perspective on the singular value decomposition as we go, but remember that decomposition provides us a way to decompose the input vector space and the output vector space, or to identify the four fundamental subspaces associated with a linear map: the range space, the null space, and the orthogonal complements to those two spaces. That's what we can extract from or obtain from the singular value decomposition. Today what we want to do is finish up the proof of this polar decomposition, which says if we have a linear operator, then we can find an isometry, S, such that we can decompose that linear operator T into a rotation or an isometry and a scaling, where the scaling now is the positive square root of T dagger T, where T dagger is the adjoint of the original map T. And we've already shown that T dagger T, or the square root of T dagger T, preserves the scaling of the linear operator itself T. And we did that by looking or comparing the norm squared of TV with the norm, or showing that in fact it ends up being equivalent or the same as the norm squared of the positive square root of T dagger T. And we used some of our insight into the inner product and what we can do relative to the inner product and the adjoint operation. But TV's norm squared is just the inner product of TV with itself. But then we can write T as T dagger dagger, and now we can shift that second slot operator back into the first slot, producing T dagger T, but now that's a positive operator, which allows us to factor it into its unique positive square roots, the square root of T dagger T. And once we have this factored form of the linear operator and the knowledge that this positive square root of T dagger T is self-adjoint, we can slide it over into the second slot again. And now with that, we see the same vector in the first slot and the second slot, and that allows us then to say, oh, that's the same or equal to the norm squared of the positive square root of T dagger T. That looks more like a plus sign in the bottom. I guess my tail was getting a little bit short. That's supposed to be a dagger. So that's T dagger T operating on V. The norm of that squared is the same as TV squared, and really what that's saying is that whatever T does as far as expanding and contracting in the various directions, that's preserved when we look at the square root of T dagger T, because this is true for any vector V in our vector space. That being said, so that's what I'm saying at the very end, that operator, the positive square root of T dagger T, maintains the same scaling. It may not maintain rotational information, and that's why we have to then say, oh, let's rotate around so that we can actually obtain the same map T in terms of this scaling piece that we've now identified and want to factor out. Meaning our next objective is to show that we can create this isometry S that makes up the other part of this decomposition of a linear operator, which we're calling now the polar decomposition. And when we say polar, that hopefully will help you be thinking about a generic complex number in polar form. Complex number we can write in rectangular form, x plus j y, or we can write it in polar form, r at an angle theta, or r e to the j theta. And we want it in the polar form to provide us with this analogy for our linear operator T that allows us now to think of that linear operator as expanding and contracting and rotating. We've now shown that the scaling is preserved by the one part of our decomposition. Now what we want to do is create this isometry that does the rotating. And we'll do that really sort of in two steps. One step is to rotate the range of the positive square root of T dagger T into or around into the direction of the range of T. And the reason we have it in two parts is if the range of t does not fill up the entire output vector space. If it doesn't fill up the entire output vector space, then we have the orthogonal complement to the range of that operator to worry about, and we'll build another rotation, S sub 2, so that we can now complete this isometry S, and it'll be made up of two pieces. One rotation that's working on the range of the positive square root of t dagger t, and another rotation that works on that space's orthogonal complement. Last time we've already looked at S1 being well defined, meaning hopefully we have some uniqueness. If we have the positive square root of t dagger t v1 equal to the positive square root of t dagger t v2, then we better be able to show that t v1 is the same as t v2, or that those two are identical. If we can't, then we can't really go any further with this. If we didn't have uniqueness, it would be hard to be talking about this polar decomposition. And this we did by simply starting with this norm of the difference between TV1 and TV2. But T, again, is a linear operator, which allows us now to factor it out of V1 minus V sub 2. And we've already shown the equivalence, or that these norms are preserved between T and the positive square root of T dagger T, which allows us now to write this second equality relationship between the left-hand side and the right-hand side. But this positive operator, positive square root of T dagger T, is linear, and we can distribute it through the V1 minus V2 to break it up into two pieces. But that was our original assumption, that those were the same, so that now when we take one from the other, that gives us the zero vector. The norm of the zero vector is 0. Now that we end up with the norm of the left-hand side being 0, we know that that has to be, because the definiteness of our norm, that now tells us that that's the zero vector inside that leftmost norm. And if that's the zero vector, then TV1 minus TV2 is that zero vector, which now allows us to add and subtract to show that, in fact, TV1 is equal to TV2 if the positive square root of T dagger T on V1 is the same as the positive square root of T dagger T on V sub 2. Those we've already talked about. What we want to do now, we know that the map is unique. Let's check linearity of that map. And if we have a map that's linear, what parts do we need to have for that map to be linear? Or what kind of properties do we need it to possess? We need homogeneity and additivity. So if we look at homogeneity, we have S1 operating on the positive square root of T dagger T applied to, let's say, a scaled version of V. But simply imposing the definition of S1, we know that that's the same as T AV. We defined S1 to be this relationship, or to create this equality. That's by definition of S sub 1. But what do we know about T? We know, in fact, it's a linear operator. And we can pull that scalar outside of the argument of t. Or we can now write that as A operating on TV. But once we have that, what else do we know about TV? If we go back to the previous equality, we know that TV was defined, or we know how S1 was defined in terms of TV, meaning we can now rewrite this as A times S1 operating on the positive square root of T dagger T operating on V. But that's now showing the homogeneity property of that map of S1 applied to the positive square root of T dagger T. We can then do the similar steps applying or looking or examining additivity. If we now start with S1 applied to an S1 again as a rotation, or can be thought of like a rotation, let's now apply that to the sum of two vectors. Let's call those V1 and V sub 2. Again, by definition of S1, that's now the same or equal to T applied to V1 plus V2. That's simply TV1 plus TV2 using the linearity of T. And now let's just go back. Each of those we can write, because of the definition of S1, as S sub 1 and that's what we wanted to set out to show. This is now the additivity. So that we now know that this map, S sub 1, does produce a linear map. What we want to do now is show that what we end up with when we look at S1 and S sub 2 together in a special way, they give us this isometry S. Or we now need to show that S is an isometry. And an isometry does what? Or what are some characteristics of an isometry? It preserves those norms. And what we want to do first is let's show that we're preserving norms with the S1 map on this restricted vector space or subspace, which is the range of T. So let's show that the norm of S1U is equal to the norm of U for all U that belong to the range of the positive square root of T dagger T, and that will then tell us that on that subspace of the range of the positive square root of T dagger T, that S1 is an isometry. And we'll do this, we'll show that using a couple of results, 746 and 747. (746) says that TV's norm is equal to the norm of the positive square root of t dagger tv, and 747 says that S1 positive square root of t dagger tv is equal to tv. Those we've already shown, and we now are labeling those when we want to do this verification. That we preserve the norms between t and the positive square root of t dagger t, and we defined S1 to give us that second equality. So those are our equations that we want to use to try to show that we can preserve norms on the range of the positive square root of t dagger t using S sub 1. Let's start then with t applied to v. But that argument of that norm we can insert or replace with the second equality using equation 747. Or that's now equal to S1 operating on the positive square root of t dagger t v. Where this and that are possible because of equation 747. But now using equation 746 allows us to also rewrite the left-hand side with the positive, or the norm of the positive square root of t dagger t v. This equality right here is coming or is allowed by 746. That's just this equality of the norms between t and the positive square root of t dagger t. And now what we want to do is realize that if we call this u and this u, that u now belongs to the range of t, and now we can say then that seeing that, we now can say that S1u's norm is equal to the norm of u on the range of the positive square root of t dagger t. So that now we have this S1 applied to u's norm the same as the norm of u. So that that now tells us on this restricted subspace of the range of the square root of t dagger t, we have S1 giving us this norm preservation that we want. Or S1 we can think of as being injective on that subspace. So we have to restrict our attention to only that subspace in case it's not the entire output vector space, but on that subspace S1 is injected. So if we take u, a non-zero vector, in the range of the square root of t dagger t, then S1 mapped, or using that map on u, does not map to the zero vector. Or that now allows us to say something about dimensions. We now can say that the dimension of the range of the positive square root of t dagger t is equal to the dimension of the range of t. And once we have that piece, now we can equate the orthogonal complements of each of those two vector spaces. Or now we can say that the dimension of the range of the orthogonal complement of T dagger T is actually equal to, do I have enough parentheses? Maybe I shouldn't have taken the range of this. Anyway, hopefully you can follow that. I think my orthogonal complement is okay there. That dimension is the same as the dimension of the range of T's orthogonal complement. And once we have the dimensions the same, we can actually find orthonormal basis on each of those vector spaces. Orthonormal basis on the range of the positive square root of T dagger T and the range of the orthogonal complement of the range of T, those have the same number of basis vectors, or they have the same length. And that's actually critical. Now we can select or choose different basis vectors, let's say Michigan of those, on the first vector space, which is the orthogonal complement of the range space of the positive square root of T dagger T. And let's pick another possible different orthonormal basis set, but it also is the same length, m in size, on the range of T's orthogonal complement. And now that we have those two bases, now we can rotate back and forth between those. Let's now define, just like we defined a map S1 to take us from the range of the positive square root of T dagger T into the range of T, now let's define another rotation, S sub 2, that will take us from the range, or the orthogonal complement of the range of the positive square root of T dagger T into the orthogonal complement of the range of T. And since they're the same size, that makes sense. Let's now define another map S sub 2 that allows us to go A1, E1, A sub 2, E sub 2. Here's an arbitrary vector that is living where? That's now in this orthogonal complement of the range of the positive square root of T dagger T. That's a mouthful, so say that about 6 times and you'll fall asleep. Well, no, maybe that keeps you awake. I don't know. It depends on how you process that information. But this is now a vector on an arbitrary vector on the orthogonal complement of the first space, which is the orthogonal complement of the range of the positive square root of T dagger T. Let's define that map S sub 2 such that it maps that vector into an A1 F1 plus an A sub 2 F sub 2 plus an A sub m F sub n. And with that definition, now S sub 2 does the mapping that we want. It maps from the orthogonal complement of the range of the positive square root of t dagger t to the orthogonal complement of the range of t. And we've defined this map, S sub 2, this rotation, to where these coefficients that weight the two different sets of orthonormal basis vectors the same, or it's using the same coefficients. So the weighting coefficients A1, A sub 2, A sub m are the same. So we're defining the map S sub 2 to make this happen. That's by definition. We have two sets of orthonormal basis vectors, E's and F's, and now we want to define a rotation S sub 2 that preserves this relationship. Now, let's use that definition to say something about the norm squared of these two sides of that equality in that definition. From the definition of S sub 2, we can now say the following. We have the norm squared of S sub 2, let's say A1 E1 plus A sub 2 E2 plus A sub m E sub m, that squared, that's just a vector, but that argument of that norm squared by definition is equal to the vector on the right hand side. So that has to equal the norm squared of that vector on the right hand side by definition of S sub 2. Or this is now equal to the norm squared of A1 F1 plus A sub 2 F sub 2 plus A sub m F sub m, that vector squared. Now, I'm suggesting that we know how to simplify this right-hand side. Remember what the F's are. The F's are an orthonormal set of basis vectors. What happens when we find the norm squared of a weighted set of orthonormal basis vectors? We just look at the absolute values of those scalars and square or add the sum of those squares of those scalars. Since what? F1, F2, if we form the inner product of F1 and F2, because you could do this in the long form, right? That norm squared is just this inner product of that with itself. But F1 and F2, F1 to any of the other F's, their inner product is 0, F1 with itself is 1, and what falls out then is we have the absolute value because we have the scalar times its conjugate resulting or falling out for each of these weighting coefficients. This now becomes A sub 2 squared all the way down to A sub m absolute value squared. This is from Sum Proposition. I hope I get the right number. In chapter 6. But if we call this vector W, what do we know about this most recent right-hand side in terms of its relationship to W, the vector W? What if we found the norm squared of W? What would it equal? It's exactly what we've written down, isn't it? It's the absolute value of those weighting coefficients squared. Or what I'm trying to suggest is that that sum of absolute value of the weighting coefficients squared is actually equal to what I've now labeled as that vector W's norm squared. And we can now look at both sides, or the extremes of that chain of equalities. We now can say, therefore, the norm of S sub 2 applied to W is equal to the norm of W, but we do have to restrict that W. W now is living where? It's in this orthogonal complement of the range space of the positive square root of T dagger T. So W is coming from the orthogonal complement of the range space of T dagger T. But that's a nice result now, isn't it, on that other orthogonal subspace to the range of the positive square root of T dagger T. Now we have an operator that does the same thing that S1 did on the earlier vector space, or between the other vector spaces. Or now we can think of S sub 2 is injective and an isometry as long as we restrict that injective and isometry behavior on this range space of the positive square root of T dagger T's orthogonal complement. And now we have these rotations that we want. They're just now two different rotations, an S1 rotation and an S2 rotation, but luckily they're happening on orthogonal complements. S1 is on the positive square root, or the range of the positive square root of T dagger T. S2 is on the orthogonal complement of that. Now we can define S as the combination of S1 and S2. Now define the ultimate operator that we were after, which was S. That is, we have S1 on the range of the positive square root of T dagger T, and S sub 2 on the orthogonal complement to that range space. Now we can pick, or you give me a vector, and because of this orthogonal decomposition, now I can do a direct sum decomposition of that vector. A part of that vector will be in the first vector space, the range of the positive square root of T dagger T, and the other part, if it exists, will be in the orthogonal complement to that range space. Let me try to write that down. Because there is a direct sum relationship between those two vector spaces, the range of the positive square root of T dagger T and its orthogonal complement, then any vector v in our input vector space can be decomposed, can be written as v is equal to u plus w, with u living in the first vector space. Let's say that's now in the range of the positive square root of t dagger t, and w is in the orthogonal complement to that. Meaning you give me an arbitrary vector, v, and if I want to now rotate it or do an isometry, maybe we haven't shown that it's an isometry yet, but we want to apply s to that. We now say we have SV. Well, because of the way that we are decomposing v into these direct sum decomposition of a vector u and a vector w, we can now break this into S1 operating on u, because S1 only operates on vectors in the range of the positive square root of t dagger t, in addition to this rotation S sub 2 applied to vectors in the orthogonal complement of that. So that's how we're defining S in two pieces. What happens now when we look at S and the positive square root of t dagger t applied to this vector v? Now we have S applied to the positive square root of t dagger t on v, but where is the output of that inner argument in the square brackets? Where does it live? Where does this vector live? That's almost a trivial question. It lives in the range of that operator, doesn't it? Of the positive square root of t dagger t. So this is in the a vector in the range of the positive square root of t dagger t. Well, if that's the case, what do we know is happening with respect to S applied to that vector? S now looks just like S1, doesn't it? Restricted to that vector space. So we can now say that this is equal to S1 operating on the same vector, the positive square root of t dagger t v. But now how did we define that? We defined S1 such that this most recent term on the right is now equal to t applied to v. And this decomposition is true or works for all of our vectors v in our underlying vector space capital V. Or we now have this linear operator S positive square root of t dagger t giving us the result that we want. It now gives us TV, but is S an isometry? We still haven't shown that yet. We've built it up to where we hope it is, but let's just verify that. But is this new operator that we're calling S, is S an isometry? If we can show that, then we're going to be finished with this polar decomposition. So let's look at that. We have now, if we looked at SV's norm squared, SV, we said, is the same as this combination of S1 and S2 applied to a direct sum decomposition of the vector V. V we split into two pieces, a U piece and a W piece. Or we now have S1U plus S sub 2W. That's by definition of S. So let's look at this. This we can go back to square one and form this as an inner product. We can now say, oh, that's S1U plus S sub 2W inner product with itself, which is S1U plus S sub 2W. And just to be thorough, let's go ahead and form all of those inner products, because we know how the linear or the inner product operation works. We can now break this into four separate inner products. We have S1U with S1U, and let's just write the last one. We have S2W with S sub 2W. Whoops, that's not equal. Well, it is, but let me not go there yet. So did you guys learn how to multiply two terms? FOIL, first, inner, outer, last. Anyway, using that, what is next? We now have S1U with S sub 2W, and we have S sub 2W with S1U. But what can we say about the last, well, terms 3 and 4 in that most recent expression? What do we know about U and W as vectors? Where did they live? They're in vector spaces that are orthogonal complements of each other, aren't they? So in fact, U and W are orthogonal. And what do we know about these S's? Those S's were actually isometries restricted to those underlying vector spaces, but they then, if they're isometries, they preserve inner products, don't they? So an S1U, S2W is, we can think of as like being the inner product of U and W, because the S's preserve inner products. So let me say and S1 and S sub 2 are isometries on their respective restrictions, and because they are isometries, they preserve orthonormality or inner products, whichever way it's going to help us do this. And that was, I hope you can verify that. That was somewhere back in an earlier theorem. Let's say it was theorem 42. But if that's the case, if U and W are orthogonal, so before we really apply that, we need to remember that S1 and S2 are isometries, so that we can now rewrite S1U comma S2W as the inner product of U and W. But now that we have the inner product of U and W and they're orthogonal, that's 0, as is this. And now what do we have on the right-hand side? We just have 2 of those 4 terms left, and those are now having the same vectors in the first and second slot. Or we now can say that we or ending up with on the right-hand side, S1U squared plus S sub 2W squared, and that was, if we find out what we started with, that was now this norm of SV quantity squared. But we know that those S1s and S2s are isometries by construction, which allows us now to do what? Just get rid of those S's in that norm. So, but S sub 1 and S sub 2 are isometries restricted to those particular vector spaces by construction, which now allows us to say that if we have SV squared equal to S1U squared plus S sub 2W squared, we can now write that as U squared plus W squared. But what do we know about V and U and W? V was equal to U plus W, but U and W were orthogonal. So now we go back to Pythagorean, don't we? We now have two pieces of this overall vector V. We have a U piece and a W piece that are orthogonal. Now we're writing V in terms of those, and we know what? Now we can go back to our ABCs. We know A squared plus B squared is equal to C squared. That's Pythagorean, and that's what is true relative to V, U, and W. If V is equal to U plus W, which it is, then if we wanted the norm squared of V, that's equal to U squared's norm, or the norm of U squared plus the norm of W squared. Or this right-hand side is now the same as the norm of V squared. And now what? Now we just need to look a little bit above, and we see that the norm of SV squared is equal to the norm of V squared. What's that say about S? Now S is what we wanted, or what we set out in this most recent piece to show, and that is S is an isometry. Now we can take a collective sigh of relief, right? We've now shown that for any linear operator T, we can decompose it as a rotation, an isometry, and a positive square root of T dagger T, or as a scaling piece. And we know how each of those two pieces works. We can think of the positive square root of T dagger T as this scaling, and S as a rotation. Does S change the norm of our vector? No. So any linear operator, that's T, any linear operator can be decomposed as a product of an isometry and a positive operator. And now we can think in terms of those two pieces. We can understand how these classes of operators work. We have a class of operators that are isometries, and we have a class that are positive operators. And we know how those both classes work, and now we can think about combining those to give us the operation of any linear operator. So we can apply that understanding to gain knowledge of any general operators. What we have to remember, though, is that note that basis where these operators in our decomposition, the isometry and the positive operator, note that the basis where these operators have nice representations or where they can be diagonalized may not be the same. We maybe can't simultaneously diagonalize the positive operator and the rotation, but that's okay. Note that basis where these operators have nice representations may not be the same, which is really what's going to lead us to our next result, which is singular value decomposition. We need two sets of bases to describe a generic linear map. However, but also can be viewed as a statement we were dealing with linear operators, but those linear operators, we can find the matrix representation of those linear operators, and so now we can think of a matrix factorization like we've just introduced for these linear operators. Can also be viewed as a statement about matrix factorization. Any matrix can be factored into two matrices, where one matrix factor has eigenvalues. If this is the factor that doesn't do anything to the scaling, what do we know about the magnitudes of these eigenvalues for that factor? Each of those now has eigenvalues with magnitude equal to 1. And the other matrix is this positive matrix, which now has non-negative eigenvalues. And one matrix has non-negative eigenvalues. Question? So now our first matrix in this decomposition of a matrix, a generic, let's say, square matrix, we now have one that's doing this rotation. That's now going to have eigenvalues that are equal to 1. And we have another matrix that could be singular. The first one's not singular, but the second one could be because we now have non-negative eigenvalues. We could have eigenvalues that are 0. And it really only makes sense to talk about these eigenvalues when we have square matrices. So here, any square, maybe what I should say is any square matrix can be factored into two matrices. We will get to generic matrices in a minute when we deal about or start talking about singular value decomposition. But now, in polar decomposition, now that we have this ability to factor a square matrix, and we were calling that a polar decomposition, the second factor, the positive operator, was associated with this positive square root of t dagger t. And we actually are going to introduce some new terminology based on this operator, this positive square root of t dagger t. We are going to call the eigenvalues of the matrix representation. Now I'm getting a little bit sloppy, but we call the eigenvalues of the positive square root of t dagger t the singular values of our operator t. And now, if we are dealing with the eigenvalues of this particular positive square root of t dagger t, we can make some generalizations about the singular values of the operator t. Since the positive square root of t dagger t is positive, what do we know about the eigenvalues of a positive matrix? They're non-negative, aren't they? They're 0 or positive. So that tells us something about the characteristic of the singular values of t. They can't be negative. So since the positive square root of t dagger t is positive, singular values of t are always non-negative. And they're real, aren't they? We also can say something about the multiplicity of those, where we will repeat each eigenvalue of the positive square root of t dagger t such that it's equal to the dimension of the null space of the positive square root of t dagger t minus lambda sub I. Where we might call this m sub I. That's how many times we repeat the eigenvalue. It depends on the dimension of the null space of that particular eigenvalue. So that will tell us how many singular values we have of our matrix T. Let's look at an example before we get too caught up in singular values and singular value decomposition. Let's just look at an example and talk about singular values, not so much the decomposition. Let's just right now focus on singular values. And singular values are this concept of scaling. They tell us the way that that linear operator, or it will be generalized to a linear map, expands and contracts in particular directions. So our singular values are either 0 or something positive. But that positive could be collapsing by meaning it's less than 1, or it could be expanding. It could be greater than 1. Suppose we look at the following. Suppose we now say that we have a linear operator, and it's now t, z1, z2, z3, z4. It now has 4 coordinates, and suppose now it maps that 4 vector into the first coordinate is 0, the second coordinate is 3z1, the second coordinate is 2z sub 2, and the fourth coordinate is minus 3z sub 4. Now the nice thing about this is we can start to exercise our memory or our recall. What's the matrix representation of T look like for that linear operator? How big is it, first of all? It's 4 by 4, isn't it? And what's the top row look like? That's all zeros. We want the output to give us 0 in the first coordinate when we hit this matrix representation, or apply this matrix representation to the 4 vectors, z1, z2, z3, z4. What's the second row? So it will now be 3, 0, 0, 0. It needs to pull off the first coordinate of our z vector. What about the third row? It's now pulling off the second coordinate, or it's now 0, 2, 0, 0. And what about the last? It's simply scaling the last coordinate by a minus 3. So this now does have some sign to it. Can you tell me anything about the eigenvalues of the matrix representation of T? And if you've had any linear algebra, you would be saying, oh, I wish my final exam was that easy. What is this matrix representation of T in shape-wise? And if I say triangle, is it upper triangular? Is it lower triangular? It's lower triangular. Everything's below the diagonal. So now what do we know about the eigenvalues? All of our eigenvalues are on the diagonal. And in terms of distinct eigenvalues, we just have a 0 eigenvalue and an eigenvalue that's minus 3. Right? 3 is repeated. 0 is repeated 3 times. But let's just say the eigenvalues, as far as distinct, are 0 and minus 3. What's the matrix representation of T dagger? Now that I've slid T off, that's not fair. So let me try to get T still showing. And what's the matrix representation of T dagger? It's just the transpose of the matrix of T, right? So now I have in the first column, I have 4 zeros. In the second column, I have 3 on top of 3 zeros. And in the third column, I have a 2 in the second row. And in the fourth column, I still have that minus 3. And now if we wanted to take this back into the form of a linear operator, what would this look like? T dagger, the adjoint of T, now has, what are its 4 coordinate entries? Do I have a non-zero first coordinate generically? Isn't it 3z sub 2? What's my second coordinate? 2z sub 3. What about my third coordinate? That one's 0. And what about my fourth coordinate? See how all this is fitting together? Now what can we do? Now we can actually form the matrix representation of T dagger T. And now you can just put those two front to back with T dagger in front of T, and what's going to happen? Well, the first column will be the second column of T dagger scaled by 3. Do you see that? Or now that's going to be 9, 0, 0, 0. The second column will be the third column scaled by 2, which now gives me a 4 in the 2, 2 entry. And the third column is going to be nothing. And the fourth column is minus 3, scaling the fourth column. If we wanted to look at T dagger T as an operator, what does that look like? We good with that? Now it should be clear how to find the positive square root of that. Luckily, those are nice squares, so that I now have 3, z1, 2, z2, 0, and 3, z4. So now it may not be, the question was, is T dagger T going to be diagonal, but what do you know T dagger T is going to be? Symmetric, isn't it? So now it will have real eigenvalues. Positive, non-negative real eigenvalues. So yes, this is a little bit cooked up, but it's easier to talk through. But now we have that for our positive square root. What are the eigenvalues of the positive square root of T dagger T? Well, if we go to here, the eigenvalues of that, that's a diagonal matrix. They're right there on the diagonal. What do we have? We want the square root of those diagonals. So we now have a 3, a 2, and a 0. A 2 somehow came into existence when we're talking about seeing. And this one, this 3, was repeated, wasn't it? And what are the singular values? The singular values of T are the eigenvalues of the positive square root of T dagger T. The singular values of T are now 3, 3, 2, and 0. So now, even though we had eigenvalues of t, they were minus 3 and 0. We now have a little bit different look to the singular values. Now the singular values of this linear operator look a little different than the eigenvalues. Obviously, they can't be negative, and we've now created, or we have in existence, something that wasn't really there as an eigenvalue of the original operator. Now we have a 0, a 2, a 3, and a 3. So the singular values of t are the positive square roots of the eigenvalues of this matrix of t dagger t, and those are this 3, 3, 2, and 0. And what I may do off air is just write down the polar decomposition of the matrix representation of t, since you've already allowed me to go a minute over what we should be going. We were having so much fun I didn't want to stop, but we did get to the singular values, and I will now write down at the end of these notes the polar decomposition of that matrix representation of t. And I'll see you in a week. Enjoy your time away.